helps to unmute myself before I talk. All right, we should start in just any second now. And so I just want to thank everybody for coming to this session and hope you guys are having a great conference thus far and that it's been great. I just want to mention that, let's see, there is a Q&A section, I think, for you to be able to post questions, though now I'm not seeing it, so I'm questioning myself on that. But if you post questions in the chat, we can bring them up during the Q&A session. It'll be 15 minutes and then 5 minutes for questions. And so we'll go ahead and let Neev take it away on the effective action of compact objects from full GR.
All right. Okay, so this is some work about a few fundamental questions that I had about this approach to calculate in spirals. And so let me try to outline the main puzzles and ideas that I had. So a lot of you might know for calculating in spirals of binary black holes, we use post-Tyrronian theory, but in post-Tyrronian theory, it's sometimes very useful to characterize the finite size effects of the point particles in post-Tyrronian theory in terms of this effective action, which is a very formal object, but it is this it's a derivative expansion of the metric around the point particle. And so these EABs and BABs are just derivatives of the electric and magnetic curvatures. So so one of the mysteries that people have observed is that for static black holes, so for perturbed Schwarzschild black holes, in general you should have all of these coefficients, but they seem to be vanishing. And people have proposed that there are some hidden symmetries and so on, which are responsible for these coefficients vanishing, because in effective field theory approaches, there's usually a symmetry behind these vanishing constants. So this was one mystery, but at a more fundamental level, even just to understand what this formal object really means in full GR. So these are a few things that I wanted to understand better, and so I just I thought I will try to derive this effective action from full GR, right? So without making any ad hoc steps, and so that's what I'm going to try to outline today. Just this and the way I'm going to do it is first, why is that happening? Yeah. First, I'm going to do it for Minkowski space-time and a scalar field, which is the most simplest thing you can do. And then I will sort of quickly go over GR and just highlight the main differences. And then after that, I will try to explain what happens for black holes and try to answer some of the questions about the hidden symmetries. Yeah, so the idea is that we have a compact object and we want to describe it effectively using the description of the field far away from the body, right? So we want to idealize the body as a compact object, as a point particle. And so the first thing that we will do is, well, I mean, for scalar fields, we all know it's very simple how to do it. We can make everything a point particle, but I want to describe a procedure that sort of generalizes to GR. So the idea would be to separate the space-time into two parts. There's this in blue is my compact body. this pink cylinder is going to divide my space-time into two parts. It's going to be the inner region and the outer region. And I'm going to write my action, my scalar field action as a sum of the action at the inner region, in the near zone, and the far zone. Oops. Yeah. And so now if I want to minimize my action, I can sort of do it iteratively, step by step, where first I minimize only with respect to the fields in the near zone. Okay, why is that happening? Only with respect to the fields in the near zone, so only inside. Once I've minimized with respect to those fields, I get some effective action, which I can then minimize at my second step to get the full equations of motions. But at the first step itself, when I minimized it with respect to the inner fields, I get an effective action that describes my fields outside this world tube. So that gives me an effective action for a finite size world tube. But this is not useful because it depends on the full details of the compact object. And in our approximation, we want to sort of forget about the details. And we can do that by noticing that if I look at the variation of the action, then the dependence on the bulk terms are only coming in through these two lid terms, because this integral just vanishes by the equation of motion. So the sigma f and sigma I are just these lids on the top and bottom. And so if they were to cancel, then the variation of my action would depend only on the fields at the boundary, which would make which would allow me to sort of approximate and neglect the inner parts of the body. And we can do this if we're looking at periodic solutions, which is or time reversal symmetric solutions, which is what we're really interested in, because dissipative effects are known to not be able to be captured by this effective action formalism anyway. So we're only trying to get the non-dissipative terms. So we're going to assume from now on that these two bulk terms are going to cancel out because of our assumptions on the kind of solutions we're looking at. Okay, so if we make this assumption, the point is that the variation of the action does not depend on the detailed structure of the body, and therefore we can proceed to try to describe the body using only the fields far away from it. And so let's try to do this for a very simple example. Let me take a scalar field sourced by a dipole, right? And what I'm going to do is I'm going to do a spherical harmonic expansion of the scalar field on my world tube. And this is just, this is just a different tensor notation, symmetric trace-free tensor notation for spherical harmonics that I'm going to use. And because I'm going to look at a very simple case where there's only a dipole moment, I'm going to ignore everything else and keep only the dipole or L equal to 1 moments. And a simple calculation then shows that looking at the variation of the action, the variation of the action is only going to give me something like this, and then we can sort of take out the variation and we get that this effective action then is given by this particular expansion. Where here I've done an expansion in small l, and this expansion in small l is the approximation that my body is small. So if my body is small, I will at some level truncate this expansion and then take the limit. So what I'm going to do is truncate this expansion and take the limit of the world tube shrinking to 0. In principle, the world tube should never be smaller than L, but we're taking both of them to be really small. So this is a very formal limit where both of them are kind of going to 0. But I'm keeping the terms in L up to some order, and I'm going to try to ignore as many terms in R as I can. But when I do this kind of limiting procedure, this is a very formal limit. It's full of infinities. But this is the kind of infinities that we're familiar with in effective field theories. This is what gives rise to renormalization and things like that. So, we do the usual thing of absorbing these infinities into the coupling constant. The point is that we started with a well-defined object, which is the world tube. There were no infinities there. It's only when I take this limit that I get infinities. But that is still a very useful thing to do, because then we get a world line instead of a world tube. So we know how to deal with these infinities. But the simplification coming from a world line is still very nice. So once I do this limit, all of my divergences are going to sort of get absorbed into this coupling constant. And then I have this kind of a point particle action. And in this limit, the spherical harmonic moments E tilde A become the derivatives of the field at that point. So once I take this formal limit, we get the usual dipole moment effective action that we're all familiar with from electromagnetism. Yeah, so that's just that. So those are the main ideas that we're going to use to get an effective action in GR. So again, I want to stress that the effective action is only truly well defined for finite world tubes, not for a world line. But this limit, point particle limit, is formal. However, it is still very useful for calculations. So we would still like to take this limit, even though it doesn't make very much sense. Okay, so now I'm going to just highlight some of the main differences that come up in GR, since I don't have time to go into technical details. The only difference is that it's a bit of a mess. There's a lot of boundary terms that you need to take into account. There's boundary terms in the corners. There's boundary terms on the horizon, if there is one. So we have the usual Gibbons-Hawking-York boundary terms. There's other boundary terms that are described in detail in this paper here. But conceptually, it's all the same as the scalar field. So that being said, let's see what we get for static black holes. What's our effective action for a static black hole? So just by using the vacuum Einsteins and periodic boundary conditions here, I can calculate directly the action. I don't have to do the tricks that I had before for the variation. That will be used if I want to do it for a neutron star, but for vacuum, it actually turns out to be much simpler to just directly calculate this action. And what I get is this. I get this very simple looking term where there's an integral on the horizon of the surface gravity, and there's the Gibbons-Hawking-York-like term on the world tube. So there's no bulk term, there's only two surface terms. Now there's something really magical that happens. If you assume that there is a static killing vector, right? So for example, a Schwarzschild or a perturbed Schwarzschild black hole, such that there is still a static killing vector. So there's still a time symmetry, right? But it's not necessarily spherically symmetric or anything like that. So there might be some other body perturbing the space-time and so on. Well, if you assume something like that, then this particular integral of the surface gravity, well, you can just you can show that this is actually just the Komar charge associated with that time translation, and therefore this integral on the horizon becomes minus half times the integral of the mass. Right, so this mass is the Komar charge, and this d tau is the fine parameter of my killing vector field. And my second term also, I can split it into two parts. One of them is going to again give me a Komar charge, and then there's a second term which comes from this two-dimensional extrinsic curvature. So combining everything together, my effective action is going to look like the Einstein-Hilbert action minus the Komar mass times d tau plus 1 over 8 pi times this term. Now when I'm taking the UV limit, when I'm going to take the limit of my world tube going to a world line, or in other words, the limit of it being very small compared to all of the length scales, what I'm going to try to do is I'm going to shrink this world tube as much as I can. And so if I take it all the way to the horizon, this extrinsic curvature becomes the expansion of the horizon, which is 0, right? Because it's event horizon, so the expansion is 0, and therefore the only term I'm really left with is in this limit is this Einstein-Hilbert action and this mass term. So there are no tidal terms at any order at any level of approximation coming in. This is all exact as long as there is the static symmetry vector field. So there is this, people have always thought there are some hidden symmetries underlying the problem, which are setting all of these extra coefficients to 0. But here you can see here that it's only just this static killing vector that is responsible for that. And so if you have a static black hole, the effective action for that is going to be given only by this mass term. There's going to be no tidal terms. And so I thought that was a very powerful result. And then you can also sort of apply this formalism to neutron stars and try to get the effective action and the coefficients of those tidal terms for that. But I'm going to leave it here. And so just to summarize again, the point particle action, which people have used very successfully in post-Newtonian theory to calculate the inspirals, is a formal limit of the physical effective action, which you can get by excising a world tube instead of a world line. And if I shrink this world tube into a world line, this introduces a lot of divergences, which and as an effective field theorist, I can try to absorb into the coefficients and do my calculations from there. But this is a sort of in practice, people use dimensional regularization instead of using this finite world tube. If these two methods of regularization of that same infinite effective action are the same, then then both of these are equivalent. If the null generator of the horizon is a killing symmetry, right? So if there's the static killing vector which is preserving the horizon of the black hole, then the effective action is given by the associated Komar charge, which is the mass. So it's only going to be the mass term and the effective action, and therefore all of the vanishing coefficients in the action are really just coming from this symmetry. Yeah, that's all. Thank you.
All right. Great. Thank you, Neev, for that excellent talk. We have just a couple minutes for a minute or two for questions. I see that Alexander has one in the chat. Alexander, do you want to unmute and ask that question?
Sure. Can you hear me?
Yeah.
Okay. Great talk. Is it clear what happens when the killing vector is just stationary? So it's not, it should try to understand Kerr, for example.
Yeah. So when you have a stationary killing vector, your static perturbation, your time independent perturbations are not going to preserve the killing horizon nature of the horizon. So the horizon will not be a killing horizon anymore once you start perturbing it, because unless your perturbation is also preserving the axial symmetry. The horizon generator is a combination of the stationary and the axial killing vector symmetry, right? So if you break either one of those symmetries, the horizon is not going to be a killing horizon anymore. And therefore, now this sort of symmetry, the symmetry at the horizon breaks down, and this calculation becomes complicated, and you really have to use the full metric to do the calculation instead of relying on this Komar chart simplifications. So if you can get the full metric, then sure, you can proceed and calculate it similar to what I'd done for the scalar field. But without that, the horizon is not a killing horizon anymore, and therefore, yeah, it doesn't work.
Okay, thank you.
All right, great. With that, let's thank Neev one more time, and I'll point any further questions to the chat, and Neev can respond if he sees them.
Okay.
All right,
thank you.
So let's welcome Rohit, who's going to talk about systematic biases away from GR due to missing the spin precession in gravitational waveforms.
Thank you. All right. Thank you for giving me this opportunity to speak. Today, I'll be talking about systematic bias away from GR due to missing spin precession or eccentricity or higher modes in gravitational waveforms. So this is a project that I've been doing with my advisor, Nico Yunus at UIUC, and also with Caitlin Prokop, who's a summer REU student. Today, I'll be focusing on the bias due to spin precession, but we're also working on bias due to eccentricity and higher modes. And this is a project that we've been doing for the last couple of months, and then we're hoping to wrap this up sometime in August, and in September, hopefully our paper will be out. So the motivation behind this talk is the need for accurate waveform models. So there's been a lot of work in developing accurate waveforms that account for spin precession, eccentricity, and higher modes. In recent years, there's been work in combining effects of spin precession with effects of higher modes. But there's still a lot of work that needs to be done in modeling eccentricity. For instance, if you look at Poissonian in-spiral waveforms that model eccentricity to 3.5 Poissonian order, they're valid to very high eccentricities, but then they don't have the merger ring down component. And models that include in-spiral merger ring down that have eccentricity are only valid to small eccentricity. And they typically don't include effects of spin precession or higher modes. And why is this an issue? Well, when you go to advanced detectors, there's a chance that you might observe sources that have effects of spin precession and eccentricity and higher modes. And there's a need to then build accurate waveforms that capture all of these effects. And for space-based detectors, there's actually further systematics that have to be taken into account. For instance, there's a chance to observe binaries with some astrophysical environment. One example of such an environment is the presence of a third body. So your binary could be in a hierarchical triple, where there could be things like Kozelidov oscillations, or there could be, instead of a third body, there could be some dark matter field, in which case you need to build waveform models that capture these effects. And I believe that later in the session, we're going to hear about effects of third body. And the bottom line is that there is a lot of effects that are not accounted for in our current catalog of waveform models. And it is important to build these waveform models looking ahead at future detectors. So what happens if you don't include these physics and astrophysical effects in your waveform model? The main point is that if you don't include these effects, you're going to be biased in your recovery of source parameters, such as the chirp mass and symmetric mass ratio. For instance, there has been recent papers that have looked at effects due to missing higher Poissonian orders. So for example, Owen and collaborators looked at what happens if you don't include higher Poissonian terms and found that there's actually a lot of significant systematic bias if you do that. Fawata, for example, looked at effects of neutron star systematics in gravitational waveform modeling. So there's a question as to what happens. So how significant are these systematic errors? Can they bias our tests of GR? One of the ways that we've been testing GR is through parameterized tests. So how would the fact that you're missing physics or astrophysics affect these parameterized tests? And the goal of this project is to address this particular question through a proof of principle study. And this is similar to other projects that people have done in the last few years, where they've looked at the impact of not including eccentricity or higher modes on the parameterized tests of GR. And our work is going to focus on what happens if you don't include spin precession or eccentricity or higher modes. And essentially what we do is that we inject a signal that has spin precession or eccentricity or higher modes. And then we recover with a signal that is essentially, it doesn't have those effects. So it's a quasi-circular, non-precessing, dominant mode waveform model, but we're going to add parameterized deviations. And we're going to study what happens to the recovery of that parameterized deviation. And this would tell us how does missing spin precession or eccentricity or higher modes impact such parameterized tests. And we do this in a fully Bayesian analysis on synthetic data using Markov chain Monte Carlo method. And this ensures that we have a robust exploration of the parameter space, and also allows us to understand how the bias depends on important source parameters. Now, and speaking of that, I want to discuss a little bit about how exactly this bias depends on source parameters and also on the detector network. So I'm going to use spin precession as an example here. So we know that spin precession effects are stronger for systems where the individual spins of your binary are highly misaligned with the orbital angular momentum. It is also enhanced for edge-on systems. And if your system has a lower mass compared to one with a higher mass, you're going to see a longer in-spiral, which allows for greater precession cycles. So spin precession effects are going to be more significant for lower mass systems compared to higher mass systems. So these are all things that we know, and we're going to leverage this in our systematic study. So the questions that we want to answer are, how does the systematic bias change if we vary the in-plane spin components, the inclination, and the total mass? And how much is, and how biased are the different parameterized deviations? So we're going to use the parameterized deviations in the framework of PPE, which is the parameterized post-Einsteinian framework. And the way that we characterize the bias is that if your recovery of the PPE parameter, if that posterior distribution does not contain 0 within 90% confidence, then we call that as a significant bias. And it's also important to address the nature of the bias. For example, how does this depend on the priors that we provide on these parameters? Does the recovery of this model actually, does the model with PPE, is that actually favored over a model without PPE, which is just a GR waveform model? So we need to characterize the nature of such systematic biases. So these are the questions that our study aims to answer. And now I'm going to go and explain a little bit more about our setup of our Bayesian analysis pipeline. So again, I'm going to explain this in the context of spin precession, but the framework is fairly general, and we can do this for eccentricity or even higher modes. So for injections, we're going to use IMR phenom PV3, which is a doubly precessing waveform model, and we use Bilby to generate these injections. And we inject into, currently we are focusing on second generation detectors. So we inject a spin precessing waveform into LVK at design sensitivity. And we use IMR phenom D and IMR phenom D with 1 PPE deviation as our recovery model. So for each injection, we always recover with IMR phenom D and IMR phenom D plus PPE. And the way that we do this parameter estimation is making use of parallel tempering Monte Carlo, Markov chain Monte Carlo method. And this is implemented in GW analysis tools that was developed by Dr. Scott Perkins, who was a former student of Nico Yunus. And I want to now explain, I want to highlight some of our preliminary results in using this injection recovery study. So we're going to first focus on the -1 PN deviation for a precessing 20 solar mass edge-on injection. So these are the parameters. So the injection is edge-on, so it's pi halves. The masses M1 and M2 are 8 and 12. And we inject at an SNR of 30. And the X component of the primary mass, or sorry, X component of mass 1 is 0.9. And we essentially set the in-plane components, the other in-plane components to 0. So this gives a chi-p of 0.9. So it's a highly precessing binary signal. So first, I'm going to show you what the GR recovery looks like. So this is the recovery with just IMR phenom D. And we see that, and I'm only showing the subspace of chirp mass and iota in this particular plot. And we see that the recovery of chirp mass is very significantly biased. The injection lies outside the 90% credible intervals, which are given by the dashed lines. And so this already tells us that there should be some impact of this bias on your parameterized test. So let's see what happens if you now recover with IMR phenom D plus PPE. We see that here again, we are recovering for a -1 PN deviation. And because the PPE parameter is strongly correlated with chirp mass, the PPE recovery is significantly biased. So the injection value, because we are assuming GR, the injected value is 0, and 0 lies outside the 90% credible intervals of the marginalized PPE, of the marginalized -1 PN deviation. And so this is a case of strong systematic bias, and we see that such a bias can contaminate your test of GR. And this is kind of one of our main results. And this is something that one could expect, but we know exactly for which systems this happens. And the goal next is to see how this bias depends on the source parameters and which PP and how this bias changes if we change the PP parameter. So right now, I'm going to show you what happens. How does this bias change if we change the inclination angle? So this is for an injection of pi halves. So we inject with different values of chi-p. So the parameter that we actually change is the X component of mass 1, and we change it from 0 to 0.9. So we pick 3 different points. So we inject with 0, we inject with 0.45, and with 0.9. And we keep the inclination fixed for now. And we see that the recovered -1 PN parameter, along with the error bars, is plotted on this x-axis, on the y-axis. And we see that the lower bound, lower 90% confidence, it crosses 0 at a value of around 0.3. So what this tells us is that when chi-p is larger than about 0.3, you are significantly biased. So even for moderate precession, your test of GR can get contaminated if the source is an edge-on signal. And if the signal is instead face-on, we see that even if the signal has a lot of precession, so if you go all the way up to chi-p of 0.9, there is no significant bias. So your test of GR is not contaminated, even though the source was precessing, but you used a non-precessing waveform. So that's another important takeaway. And finally, I'm going to show you now what happens if you change the total mass of the system. So the earlier injections were for a total mass of 20. So if I increase the total mass to 40, that means that there's going to be fewer precession cycles. And again, if I change chi-p from 0 to 0.9, we see that there's no significant bias. And this is for a case of an edge-on signal. So there is a lot of precession, but because because the mass is now heavier, there's fewer cycles, and you're not significantly biased. So your test of GR is okay. Now, we need to characterize the nature of this bias. And the way we do this is we look at the Bayes factor in favor of a GR model over a PPE model. So the Bayes factor, the log Bayes factor is given by the log evidence in favor of GR minus the log evidence in favor of the PPE model. And I'm plotting the log Bayes factor for different chi-p values. And what we see is that the GR model is essentially favored in all cases. And this is for the edge-on case for 20 solar mass. And if you remember, for a chi-p of 0.9, there was significant bias in the source, in the recovery. So why is it that the Bayes factor favors GR? The reason is that the Bayes factor depends on the prior, and the priors we used were wide uniform priors on the PPE parameter. And because the -1 PN parameter is very tightly constrained, you incur a large Occam penalty when computing the Bayes factor. So even when you're significantly biased, you're still, the GR model is still preferred. And so this is an example of what we call as a stealth systematic bias, meaning that you are in principle biased, but then the GR model is still favored over the PPE model. But because this depends on the prior, it's important to account for, it's important to use more informative priors. And so we're going to repeat this analysis by using a prior that includes the asymptotic property of the Poissonian series. So meaning we expect that in the phase, higher PN terms are going to be subdominant compared to lower PN terms. And the goal is to repeat this analysis and figure out how does the Bayes factor change as you change the injected precession. And we expect to find that when you include this prior, we expect that the Bayes factor should result in a conclusive systematic bias. And with that, I will bring you to my summary. So the main takeaway of this talk is that unmodeled spin precession can bias your parameterized test of GR. And the test of -1 PN deviation is robust for moderate inclinations and for higher mass systems. Currently, we are working on looking at the bias in the 0 PN, 1 PN, and 2 PN deviations for spin precessing injections. And like I said, we are looking at the nature of the bias, characterizing whether the bias is a stealth bias or not. And we're also looking at the bias due to missing eccentricity and higher modes. And with that, I will end my talk. Thank you.
All right. Thank you, Rohit. That was great. We have just a couple minutes for questions. Does anybody have any that they want to ask? I don't see any comments in the chat yet. Oh, we've got a raised hand. All right. Vinci, do you want to go ahead?
Yeah. Hey, Rohit, nice talk.
Hey.
I was wondering, do you plan to, I think you mentioned at the introduction, Lisa, do you plan to extend this to Lisa as well? Because I would think
yes,
you will see many more cycles there, right? So I guess
so for
even more important.
Yeah, that's a very good point. And we are planning on looking at systematic biases for Lisa, but we are going to focus on different effects. So so I'm also working on looking at the effects due to a third body. So I'm modeling the effect of Kozalidov oscillations of a binary that's orbiting a third body. And we are going to use those waveforms essentially to do a very similar analysis. And so we're not, so in short, we are going to study this kind of bias for Lisa, but we're going to study different effects, if that makes sense.
Cool, thank you.
I just had one quick question, or I just think I missed it. when you were injecting with the processing system and then recovering with just IMR phenom D, were you injecting just the dominant mode? Or were you like you're recovering with just the dominant mode? Are you injecting with just the dominant mode as well?
Yeah, we're not including higher modes. Yeah.
Okay, cool.
Yeah, so all the biases,
check.
yeah, the way that we're doing it, we want to isolate the different effects. So when we want to study effects due to spin precession, we only include the dominant mode. And similarly, when we're studying effects due to higher modes, we don't include spin precession.
Okay, gotcha. Just wanted to double check that.
Yeah.
All right, cool.
Thanks.
Well, thank you so much for that great talk. And yeah. And if anybody has more questions, feel free to post them in the chat, of course. All right, so let's invite Zhongfu to talk about binaries wandering around supermassive black holes due to electromagnetism.
Okay. Hello, everyone. My name is Zhongfu Zhang from Peking University in China. My supervisor is Xian Chen. Today, I will talk about the dynamic evolution of binaries wandering around the supermassive black hole. Like Vogel have detected around 100 compact binaries. Most of binary black holes mass are larger than detected by the X-ray binary in EM counterpart. Many astrophysical channels can produce so large a mass of binary black hole in theory. Here I introduce a possibility that the mass detected by the gravitational wave is apparently large, not the real large. In gravitational wave detection, the direct observer quantities is frequency and f dot. They are the redshift, so the mass is degenerate with the redshift in gravitational wave detections. If the binary black hole orbit in the vicinity of the supermassive black hole, as shown on the left, it's easy to get a strong Doppler redshift induced by the high velocity and the gravitational redshift caused by the strong GR effect. So the normal tensor mass of the binary black hole seems like more heavier, as shown on the right. So how this system can form? On the one hand, the supermassive black hole can accelerate the merger of binary black hole by exciting in its intrinsicity due to the three bodies dynamics like Kusaridov effect, evacuation readiness. And the post-merger, the black hole is like returned in the vicinity of the supermassive black hole because due to the larger escape velocity caused by the supermassive black hole. So and it could be repeated mergers, so they can increase the binary black hole's mass. If the supermassive black hole have a gravity disk, actually in the AGN, a black hole can merge more frequently through the interaction with gas, star, and other compact object. In this figure, they summarize some interactions between the binary black hole. Finally, the merge rate could be comparable to the Lego-Vogel event rate. But if we want to detect this source, we need to know the gravitational wave template. And if we need a template, we should know the dynamics. So I introduce how to do the dynamics. Well, for the method, when the binary black hole is hundreds to thousands of gravitational radius from supermassive black hole, the velocity of binary black hole is relatively small, so we can study it using the post-Newtonian expansion with the velocity. When the binary black hole is moving around 10 times the gravitational radius, the speed already close to the light of speed. It's common to treat the binary black hole as a mass point along the geodesic, similar to the extreme mass ratio. like EMRIs. Apparently, this system is different made up a binary black hole, so it's common. We named the BMRI. As the distance decreases, the tidal force of the supermassive black hole become larger and larger. So the binary black hole could not be regarded as a particle. Besides, the strong GR effect are more different with the normal Newtonian force. For example, I show example. The spinning supermassive black hole can generate a new force, the gravitoelectromagnetic force. The force appeared as a force in different directions when we excited the intensity of binary black hole to promote the mergers. Compared to the self-gravity, we find the radius region are several gravitational radius. So post-Newtonian is not enough. We need more GRA. Here, due to the hierarchical triple system, the velocity of the central velocity in the central mass are smaller than the light speed. So we can take advantage of the equivalence principle and investigate the problem in a frame, free falling together with the binary black hole. The dynamics become in this frame. The dynamics become Keplerian plus perturbing force induced by the supermassive black hole background. Gravitoelectromagnetism is a good tool to show the perturbation. The force can be shown as the graviton-electron and graviton-magnetic force. Actually, this force not is a classical GR effect, not the GR coupling with some EM force. The objects are no effect in the central of the in the frame, like a panda in the central. You don't feel anything. You will feel anything. And if the object divides a small radius, you will feel the same direction in the graviton electron. And the velocity will cause the vertical direction the graviton magnetic force. So the object will, if we derive it a little radius, the object will be away from the center. And the graviton-magnetic field are associated with the Riemann tensor and the position in the free-fall frame. So this term we need to transform from the Bolognese coordinate, increased coordinate. So I established a free-fall frame along the circular geodesic orbit in the equatorial plane to simulate the dynamics in the AGN. So there are three depths to three depths from the Bolognese coordinate: centroid transformation, Lorentz transformation, and the spatial rotation. Especially for the spatial rotation, we can imagine a gyroscope rotated around the black hole. Here are some result. The left channel is showing the result of distance equal to 3.3 m. The black line is the central mass. Geodesic observer is in the origin at rest. So we find the central mass is not following a geodesic line. The red panel is showing the EB field. The EB is proportional to the position of the object. So the total graviton-electron force scaled with the position of the central mass, but the total graviton-magnetic force is different. It depends on the relative position and relative velocities. In general, it does not vanish. So the central mass can't follow a geodesic, it will away from. Furthermore, varying the initial conditions, we find the intrinsic of the binary black hole. The inner binary oscillated repeatedly, and it is excited to a value as large as 0.9, which indicate the strong gravitational wave energy loss. than before. So we can expect the motor time is lower. Then I compare to the post-Newtonian and Newtonian's formalism to show they are not enough to simulate this system. Besides, outer binary shows many dynamic effect like radio oscillations and the accumulated phase drift. For this system, there are the multi-band, the gravitational wave source. There are the high frequency gravitational wave caused generated by the binary black hole, and its motion around the supermassive black hole generates a low frequency one. For the inner binary, like the inner band in orbit, the binary black hole, the orbit frequency is around 10 millihertz in the rest frame. Due to the gravitational and the Doppler redshift, they find the inner binary remains in the sensitivity to the sensitivity band of LISA. The outer binary has a frequency about 1 millihertz, which may be detected by LISA. This system actually like EMRI, but it's different. We have found some deviations. When reading mismatch, maybe after 2 weeks would be enough to detect it. Actually, due to the environmental factor, it might be difficult and require more further investigations. So their summary, I introduced a new system, the compare binaries around the supermassive black hole named the EMRI, and post-Newtonian is not enough. I introduced a new system, consider the dynamic study this system in the free for frame, and this system can apply for 2 or 4 gravitational radius, and there are many dynamic effects, like the central mass of binary black hole don't follow a geodesic line, and the inner orbit, the intensity is oscillation repeatedly, and this system will be detected by LISA. So more details in our paper. So thanks.
All right, thank you so much for that excellent talk. That was really interesting. All right, looks like Rohit has a question.
Hey, thanks for the very nice talk. I have a question about the distance to the supermassive black hole. So I don't know if I got this right, but is the distance to the supermassive black hole like 2 to 3 times m? Like m is the total mass of the supermassive black hole. Is that right? So the so just to be clear, so the inner binary is at a distance of around 3 m away from the supermassive black hole?
No, this the central mass. You can see the right figures. The distance from the supermassive black hole can be several 2 or 3 m, but the inner orbit is not. Inner orbit is like
Right, but the outer orbit is, if the outer orbit is only like 3 or is around 3 m, I mean, wouldn't that orbit be unstable? Because I mean, 6 m is the ISCO of the outer orbit, right?
Actually, it's a good question, but it's stable. Why? This you see this figure, the blue line. I show the tidal stable regions. The blue. I use the health radius, and this is minus below the health radius. So this system is stable. And if I also in my simulation, if the system is not stable, we will disrupt. So the result is not stable. So we can see in the orbit. Yeah.
I see. Okay, thank you.
Okay, great question. I had one question, basically on your very last slide or second to last slide, thinking about detecting this and how it's multi-band, and you've kind of got the two different orbits that you're potentially able to detect. What do you think would be the possibilities or likelihood of being able to identify both of those different signals as kind of coming from the same system, being able to tell that both of those signals came from these binary orbiting the larger black hole?
Yeah, this is much actually, if we want to identify the system, we need the template, right? And for inner binary, there maybe in the free for frame is just the normal binary black hole the waveform, but he need to affected by the gravitational lensing effect. So it's more, we need more carefully to calculate this. So I don't know how to do this, but and for the out binary is we can compare to the standard EMRI template. So I also show some more deviations. So I think this system is easy to detect it. Yeah.
All right, great. All right, if there are more questions, feel free to ask them. Otherwise, I think we're taking a break until 10 after the hour, whatever hour it may be, wherever you are. All right, but great session so far, everybody. I've really enjoyed these talks. All right, so welcome everybody back. Hope you all had a good break. We'll go ahead and start this right off the bat so that we can keep on schedule in case people have other sessions that they want to go to as well. So let's go ahead and welcome Shubham, who's going to talk about more realistic inference of EMRI environments. Take it away.
All right, so I want to talk about more realistic inference of EMRI environments. My name is Shubham Kejriwal. I'm a first-year PhD student at the National University of Singapore under the guidance of Professor Alvin Chua. This is just to say that this is all very preliminary, and this is just to set your expectations. This is more of like a offbeat presentation in which I would be sharing about what I plan to do going ahead and what I have been working on recently, but do not expect any results right now. I joined like 5 months ago as a PhD student. But anyways, I do have some ideas to share which need focus on in this field. So why do we want to analyze EMRI environments? First of all, what are EMRIs? These are extreme mass ratio in spirals. So it's very similar to the system you see on the right side. There's a supermassive black hole, about 1 million solar masses. And then there's a small object orbiting it in very strong gravity regime. So this could be a 10 solar mass black hole, for example. And extreme mass ratio in spirals in the LISA band would be long-lived, which would be around a year or more in lifetime. And this would allow the secondary object to orbit 10 to the power 5 orbits around this supermassive black hole. What this would entail is a precise measurement of the central supermassive black hole's parameters, such as its mass and spin, and the orbit of the secondary object. However, if these environmental effects are not accounted for, or are not modeled in your system, they can modify your vacuum parameters or can introduce bias to them. This can lead to biases in your global fit, which is the prime way in which we expect LISA data analysis to be carried out. So the biases in a single EMRI can introduce biases in another EMRI, or your measurement of a supermassive black hole binary system because of the global fit system. It can give rise to false alarms for beyond GR and GR tests. It can also introduce biases in your cosmological inference, or the inference, for example, of the astrophysical distribution of black hole masses, etc. So all of that is just to say that accounting for environmental effects is a very big task and a necessary task for EMRI environments. So what is the current state of the art here? It's given by a study by Barraus et al., Enrico Barraus et al. In 2014. This was a purely dephasing based analysis, leading order to the self force. And the main conclusions here, although it's a very long paper, about 72 pages or so, the main conclusions here are that if there is any important environmental effect, it has to be the planetary migration effect based on a purely dephasing argument. As you can see, it introduces the largest dephasing effect when compared to the purely GR trajectory of the secondary's orbit. However, more importantly, it concludes that most environmental effects would be negligible for extreme mass ratio in spirals. So the story should end there, but as you'll see in the next few slides, and as I will argue here, this is probably something to be taken more skeptically than is presented in the paper. So the pros of this paper is that it's a very comprehensive analysis. The paper is quite comprehensive. Everything is given very step by step. So it's almost like a guide for EMRI environmental analyses of the future. However, the main cons that it suffers with is that the analysis is quite simplistic. So it's assuming a short shield supermassive black hole in the center, and the orbit that the secondary takes is circular and equatorial. So it's a symmetric, axisymmetric system, which is not a realistic EMRI you would find in nature. And at the same time, this dephasing argument is not enough, as is also seen by later studies. So this paper by Sperry et al. In 2022 is much more recent. It deals with a Kerr EMRI now. So the central supermassive black hole is now a spinning object. And it studies the effect of migration, which was the most important effect as concluded by Burrows et al. Previously. They studied this effect in isolation in a Kerr EMRI system using the fast EMRI waveform package. And their main conclusions was that, again, as I mentioned, dephasing is necessary but not sufficient. So it does tell you something about the significance of a particular environmental effect, but it may not be sufficient for concluding whether an effect would be detectable or not. However, they did find that in this fully Bayesian inference of their system, environmental effect of this planetary migration was indeed detectable. Again, breaking it down in a very naive sort of pros and cons list. Pros is that this is the first time a fully Bayesian inference of EMRI environments was conducted. But the cons is that a single effect has been studied. I'll talk a bit more about this in the next slide. And again, although it's a Kerr system, it's a quasi-circular and equatorial orbit of the secondary. So it's not a fully generic Kerr EMRI system that we would like to finally study in the context of environmental effects. Moving on, so now I'm going to talk about some quite ambitious things that I plan to work on in the next couple of years, and I'm already working on a few of them. I do have some preliminary results, but those are quite premature and would not be, it won't be justified to show such preliminary results in such a talk. So first of all, what I'd like to do is to make an updated hierarchy of effects following Burrows et al. Et al.'s analysis of 2014. So this is the ambitious part. Can we go to a fully generic Kerr EMRI system? So can we introduce non-equatorial eccentric orbits of the secondary around the supermassive black hole in the center? And I think it's quite reasonable to assume, although that's not the area of my group's expertise, but I believe that in the span of about a decade now from Burrows et al.'s analysis, it is possible that we have better environmental effect models as well, better accretion disk models, and better understanding of the assumptions, underlying assumptions of these accretion disk models, etc. So can we use a better environmental model to start with? And then another very big prospect here is of a joint analysis of at least two environmental effects together. And the main reason why we want to talk about joint analyses is because the same physical phenomena surrounding an extreme mass ratio in spiral can give rise to more than a single environmental effect. For example, an accretion disk, a physical phenomena around a supermassive black hole, can give rise to planetary migration, it can give rise to dynamical friction, and it can give rise to accretion. So these three are three independent environmental effects which would affect the secondary's orbit around the central black hole. So we need to study all of them simultaneously. And as far as my knowledge goes and my group's knowledge goes, there is no analysis which talks about the combination of even more than one environmental effect at the same time. So this is important, not only because it can cause higher dephasing, but because if you're doing a proper Bayesian inference, you also want to take into account correlations that come in an analysis. And if there is very tight correlations, for example, between two environmental effects or the parameters of two environments, this can make your inference of your vacuum EMRI parameters much worse. This can say something about the detectability of a single environmental effect or the combination of environmental effects, for example. And so this is something I'm focusing on right now, and I think is quite important. Going forward, I would also like to explore what are the parameter space regions in which these so-called dirty EMRI templates would become important versus a vacuum template. Why this is important is because of the curse of dimensionality. So now imagine you already have 14 plus dimensions of just a vacuum EMRI template, vacuum EMRI model. And on top of that, you are adding some n parameters due to a combination of environmental effects. So that would make your Bayesian inference, for example, for a global fit, very, very difficult. So like a workaround that would be that you can identify regions of the parameter space, like so was done in this analysis of Zwick et al. For massive black hole binaries. So these brown regions indicate regions purely again based on a dephasing argument where environmental effects would be dominant. And there are these turquoise regions where vacuum templates would be sufficient. So we can do a similar analysis, but for EMRI parameter space to say in which regions can we avoid using these dirty EMRI templates, which would make our inference a bit more efficient computationally. And finally, can we do a population study? So instead of just taking a single source, a single randomized source out of a bunch of EMRIs, can we take a bigger bird's eye perspective of the problem? Can we assume a particular population model, astrophysical model of the black hole mass distribution in the universe, or at least in the LISA observation band, and produce a more statistical overview of how many EMRIs would be affected by the environment, how much it can potentially bias our inference, etc. So this is the most ambitious out of all of the proposed upgrades I have highlighted so far. And finally, I would like to talk about some challenges I see already diving into these projects. First of all, would be consistency checks for joint analysis, because, for example, if you have two different environmental effects which are independently modeled, so I'm picking up environmental effect A from a certain paper and environmental effect B from another paper, it won't be as easy as just adding them to my fluxes of the secondaries of the evolution of the extreme mass ratio in spiral, because they may not be intrinsically consistent with each other. So I need to make sure that both of them are valid in the same region of evolution of the secondary around the central supermassive black hole, for example, and so on. So that is going to be something to take care of. Not all models may be compatible with each other. Secondly, we want to balance between the realism and the feasibility of both GR waveforms and the environments. So we want a GR waveform and we want an environmental effect which is realistic enough. As I said, we want to go to curve plus inclined orbits plus an eccentric secondary object. But at the same time, we do not want to expand our dimensionality of our model so much that we are not able to do any computational inference on it. Again, that is a little bit beyond the area of expertise of our group. So again, if anyone in this talk is interested in guiding us in this particular aspect, we'd be happy to collaborate. Thirdly, as I mentioned previously as well, there's a curse of dimensionality. So even for a single source, doing a Bayesian inference for 14 plus n dimensional EMRIs would be very difficult. And then if you want to expand it to a full astrophysical study of a population of EMRIs, yeah, that's going to be super hard to do. And finally, and the point I would like to stress upon the most is that there are systematics at all levels. There are systematics and assumptions at your EMRI model level. There are systematics and assumptions at your environmental effect model level, at the level of your astrophysical model. So at all of these levels, you need to make sure that you are not going beyond the scope of any of these models, such that you are not seeing an artifact because of a model incompatibility, and you're actually seeing a deviation from your vacuum EMRI system, for example. And I'd like to finish with this nice little comic about statistics. Thank you so much.
All right, thank you so much for that excellent talk. Any questions from the audience? Okay, I don't see any questions. So I was just wondering, I know you said you don't want to, or you don't have a lot of results to show yet, but is there anything that you would like to highlight? Any preliminary thoughts that you're most excited about that you want to share?
Sure. So right now I'm working, as I mentioned, on these joint analyses. So I am taking just from this Baraus et al. Analysis. They made this hierarchy. So I'm literally picking up these two most dominant environmental effects, the planetary migration and thin accretion disk dynamical friction effect. And I am using their parameters in together with the vacuum EMRI template. And right now I've only done a Fisher analysis. The next step is to do a full Bayesian inference. But even in this, for the Kerr circular flux model that was used in Sperry et al.'s analysis, I'm finding that there are very strong correlations which can make the precision on some of our intrinsic parameters, such as the masses and the spins of the EMRI system, worse by maybe a factor of 3, factor of 5, and especially in the case of spin, it gets worsened by about an order of magnitude. So that's the most exciting results I see right now. There is a lot of tight correlations between different parameters, and yeah, I want to do a fully Bayesian inference on that first, and then go ahead and introduce maybe a third environmental effect in them, maybe accretion onto the central black hole, for example, and see how it modifies everything. So it kind of modifies the results of Sperry et al.'s analysis, which was claiming that in isolation, just if you analyze the planetary migration effect together with the vacuum parameters, there is a scope for measuring the parameters of this planetary migration effect. But now if you introduce this dynamical friction model as well, then the posteriors flatten a lot basically, and this effect would be very basically undetectable. But again, that's very preliminary. I need to do a lot of checks on this before claiming anything. Yeah.
Sure. Well, that sounds very interesting for sure. So definitely interested to hear about it once you have more results.
Yep.
All right, let's thank Shubham again, and let's go ahead and welcome Andrew.
Right, so hi everyone. So my name's Andrew Casey-Clyde. I'm a 5th year graduate student at the University of Connecticut now. And I'm going to be talking to you about some work that I've been doing with my advisor, Chiara Mingarelli, as well as our collaborators that I've listed here, to try to answer this question I have on the screen of how many quasars host supermassive black hole binaries. You might guess from the title, this is a little bit of a different talk from the rest of the talks in this session. I apologize for that. I had a bit of a scheduling conflict. I was supposed to be in one of the stochastic background sessions on Tuesday, so get your head in that headspace. I had a bit of a conflict. I was getting married on Tuesday, so couldn't quite make it that day. But yeah, so I'm going to go ahead and try to answer this question of how many quasars host supermassive black hole binaries. So with all that kind of context out of the way, go ahead and get started here. Like I mentioned, I was supposed to be in the stochastic background talk. So if you've been hearing a bit about a stochastic background in the past few weeks, you might have guessed that I work in the pulsar timing array band, so way down here at the low end of the gravitational wave frequency spectrum that I've shown here on the right. And you might have heard, hopefully, in the past few weeks that nanograv has found, and really all the pulsar timing arrays have found evidence for a gravitational wave background. For nanograv, this was in our 15-year search, but similar results have been seen in the European pulsar timing array, the Parkes pulsar timing array, Indian pulsar timing array data, as well as the Chinese pulsar timing array. So it's a very exciting time to be in the low frequency gravitational wave regime. Now, if you've been hearing about these results, you might have also heard a little bit about supermassive black hole binaries, which is what we expect to be the main kind of source of nanohertz gravitational waves. So there's other possible exotic sources as well, but I'm not going to get into those for this talk since I'm really focused on the supermassive black hole binaries here, since we're really interested in constraining that population as much as we can. Now, in all of these recent results, we did not detect individual gravitational wave signals from individual binaries, but it's kind of what we expect, that that's going to lag our gravitational wave background signal by a few years. And so now that we have this evidence for gravitational wave background, we can say with a good degree of confidence that we expect that in the next few years, we're going to start detecting gravitational waves from individual supermassive black hole binaries, what we call continuous waves. And so in the spirit of that, this talk is basically about what we can do to try to make that process a little bit easier. And if there's anything we can do to maybe focus our searches instead of looking at the entire sky, instead see if we can focus in on particular galaxies that might be good candidates. Now, the way that we are approaching that is with quasars. The reason that we're using quasars is because we know that quasars can signpost galaxy mergers. And since a supermassive black hole binary is a natural result of a galaxy merger, it brings up this natural question of, can quasars also signpost supermassive black hole binaries? If they can, that's really cool for us, since, like I kind of alluded to, that actually helps us with things like targeted searches for supermassive black hole binaries, which have been found to be, or which are predicted to be more sensitive to gravitational waves from these continuous wave sources. And they also should be able to enable us to get much tighter constraints on the parameters of these systems, like their chirp mass, if we have a good guess on the frequency, for example, from an electromagnetic binary signature. Then, of course, if we find an actual multi-messenger supermassive black hole binary system here, that's just going to be very cool, since that'll enable all sorts of really cool multi-messenger astrophysics for us. Who knows what someone will come up with if we can start combining all of this data from an electromagnetic signature of a binary as well as the actual gravitational wave signature. So, what do we look for when we want to look for possible supermassive black hole binary candidates in electromagnetic searches? And when we're looking at quasars, what we look for currently, or at least one of the things we look for currently, are what are called quasi-periodic light curves. So the basic idea here, and I'm showing a few light curves on the right here from the Catalina Real-Time Transient Survey. So the basic idea here is that we monitor quasars and how much light they're emitting over a long period of time. And we look for these kind of sinusoidal variations in those light curves that you can see in all four of these panels here. And what we think is that those quasi-periodic oscillations might be the signature of a supermassive black hole binary. So like I said, Catalina Real-Time Transient Survey has a nice catalog of these. They have 111 supermassive black hole binary candidates identified via these quasar light curves. And they have a nice long, nice year baseline, which is one of the things that you really need when you're carrying out these search campaigns, since you need to check over a long period of time that we actually have this sinusoid in here, especially since when we're talking about nanohertz gravitational waves, we're talking periods that are on the order of anywhere from, say, maybe a few months to a decade or more. So these 9-year baselines are really a kind of starting point for these. And what we're actually very excited about for impulsar timing arrays is a few things. One, once the square kilometer array goes up, we actually expect that'll give us enough sensitivity to start really testing a lot of these candidates that we have. The Catalina Real-Time Transient Survey has 111, but there are several other catalogs, including from the Zuki Transient Facility, that also have magnetically identified candidates. So we have a good pool here that we really are hoping to start testing soon. The other thing that we're very excited about for the future is Vera Rubin LSST, which is just going to have much, much greater sensitivity. And so we're going to be able to probe these quasars to lower luminosities and out to higher redshifts, which will be great for these kinds of surveys. All right, and then I'll mention the last thing at the bottom here. So we're starting from the Catalina Real-Time Transient Survey for this work, but we expect most of the background to be encompassed by a volume of about 1.5 for redshift. So we immediately kind of cut this down, and we end up only using 87 of these candidates for the rest of the study. So we're not using every single candidate that we have available here, but I think we're using the kind of most relevant ones. All right, so how do we actually put this together and try to figure out how many quasars host supermassive black hole binaries, as well as whether quasars are even a good place to look in the first place? What we want to do is we basically just want to compare binary fractions. So on the right here, I have some kind of example mass functions, and I'll be filling in some more details as we go here. But this is basically showing the number density of, binaries or black holes, what have you. So the number density of these objects per unit, log mass, basically gives you an idea of, how many black holes, say for our black hole mass function here, should we have at different masses. And we expect that we're going to have more black holes at lower masses than we do at higher masses. And so we're going to look at a few different mass functions here, so that way we can calculate some of these fractions. The two we're particularly interested in are the binary fraction, just how many galaxies in general might host a supermassive black hole binary. That gives us a bit of a baseline. And then we want to look at the binary fraction of quasars specifically. Out of just the quasar population, how many of those also might host a binary? And then we can compare these two and try to figure out, do quasars maybe have an excess of binaries in them, or are they similar to just the general binary population, and quasars are actually a red herring in that case. I'll go through each of these mass functions in turn, starting with the supermassive black hole mass function, which I have here in green. To calculate this, we use a galaxy stellar mass function, or really a compilation of galaxy stellar mass functions from Consolis et al. 2016. We then convert that galaxy stellar mass function to a black hole mass function by basically assuming a couple of scaling relations, first from the galaxy stellar mass to the bulge mass, and then from the bulge mass to the actual black hole mass. These are all empirical scaling relations, and they give us some rough idea of, how many black holes should we expect within each mass range. And I'll note here that all of the uncertainties and shaded regions that I'm showing in my plots are 90% confidence intervals, so they might look a bit beefed up compared to any mass functions you might have seen in the past. All right, that's our black hole mass function. Next, we have our black hole binary mass function. This actually takes the exact same galaxy stellar mass function and scalings as I showed in the previous slide, and then additionally assumes a galaxy pair fraction and a galaxy merger time scale. And then we fit the whole thing to the nanograv 15-year signal. So this is actually consistent by construction with the recent results out of nanograv. This is all nice and up to date. And so the nice thing about doing it this way, and specifically the nice thing about the way we've constructed our black hole mass function, is that we're actually not assuming anything in our model that isn't already part of our black hole binary mass function. So all of our occupation fractions that we calculate here are totally self-consistent. And so this is a nice feature that's actually present in this kind of class of galaxy merger derived black hole mass functions, though we think it's been a little bit underutilized in the literature before. So we're trying to really highlight it here. The next thing that we need is a quasar mass function, since we want to try to figure out how many quasars might host a binary. For that, we use the bolometric quasar luminosity function from Xian et al. 2020. And for anyone who might be familiar with the Hopkins et al. 2007 quasar luminosity function, this is a direct update to that. Once we have our quasar luminosity function, we then assume a scaling relation between Eddington ratio and bolometric luminosity, since this implies a scaling relationship between the black hole mass and the bolometric luminosity. So it gives us a way to convert between the two. And then we convolve. Basically, at each luminosity, we calculate what's the probability that this luminosity is a black hole of some mass, say 10 to the 8.5. And then we integrate over all possible luminosities to figure out all of the different masses and relatively how many black holes we should expect at each mass. And I'll just note here that there is a little bit of a turnover in our quasar mass function. That actually just is a result of the luminosity limits we're taking, since we're limiting ourselves to the luminosity range of the CRTS sample. If we took it to lower luminosities, this would kind of go back up like you might expect for other mass functions. All right, finally, we need a binary quasar mass function. So for this, we use that population of Catalina real-time transient survey binary candidates. And then we basically assume to make some naive assumptions to place upper limits on that population. Those naive assumptions just being that, if every single quasar naively hosted a binary, how many binary quasars would we expect to see in CRTS? We compare that to how many we actually saw. And then we do the same thing for the black hole binary mass function. If every black hole binary had an associated quasar activity, how many binary quasars would we expect to see? And then we compare all of that to CRTS and say, okay, we have too many candidates in CRTS, so probably not all of these are real, but we can place some reasonable upper limits. And what we find is that we expect no more than 6 out of those 87 candidates are probably genuine. This is pretty consistent with other studies based on hydrodynamics from Kelly et al. 2019, which found no more than about 5 of the entire sample could probably be real. Then once we have that, we can then construct with our kind of reduced sample a binary quasar luminosity function, which we then treat in the exact same way as the quasar luminosity function to come up with a binary quasar mass function. We just convolve with that same scaling relationship between bolometric luminosity and Eddington ratio. So we put all that together, and then we calculate our occupation fractions. So occupation fraction, fairly straightforward to calculate. We just take how many binaries we have and we divide it by the total number of supermassive black holes that we have in all of these different mass bins. Or if we integrate all of that, what we find is that the binary occupation fraction is about 3%, but within the 90% confidence interval here, there's still quite a bit of wiggle room. It could be as low as a little under 1%, or as high as 24%. We then calculate a 95% upper limit for the binary occupation fraction of quasars. And I'll note this is necessarily an upper limit since we don't have any confirmed supermassive black hole binaries, any confirmed individual binaries at least. So this is necessarily an upper limit, and we find that upper limit is about 4%, so a little bit larger than what we might expect for our kind of median value for the binary occupation fraction. And the next slide, I'll show you how those two compare, but you can see already here that if we consider the lower limit on the binary occupation fraction with this upper limit on the binary occupation fraction of quasars, it looks like we might have binaries in quasars a little bit more often than in the general galaxy population. Though again, these are all still upper limits here. All right, so the final thing that we're doing is, just like I said, we're doing this comparison to try to answer this question: can quasars signpost binaries? And so if we compare those occupation fractions I showed on the previous slide, the conclusion that we come to is that, yes, they potentially can. In fact, quasars could host binaries up to 7 times more often than just the general galaxy population. Or put another way, if I'm looking out into the sky and just trying to, choose where I think there might be a binary, I'm choosing somewhat randomly, I'll do about 7 times better if I limit my choices to galaxies that have a quasar in them. So, quasar activity, than if I were to just choose from the entire galaxy population. So what that tells us then is that for things like targeted searches, a good place to be looking might actually be quasars, since we might expect there to be a binary there a little more often than just in galaxies in general. And then what I'm showing here on the right is how this upper limit breaks down over mass and redshift as well, since we can, look at this not just in, broadly over all masses and redshifts. We can look at specific masses and redshifts here. And we can see that for the most part, we do a little bit better for things that are closer by, as well as have a better possible signposting chance for things that are high mass. All right, so to summarize, essentially what we're finding is that quantitatively, quasars could actually signpost supermassive black hole binaries. In fact, we could do up to about 7 times better by looking at quasars than just by looking at random galaxies. And then, of course, there's a lot of room for follow-up here. The kind of big, most, I think, obvious target being, actual continuous wave constraints. If we can detect a supermassive black hole binary, that's going to tell us a lot about what these populations look like. But the other things that we're also excited about are things like Vera-Rubin LSST, which is going to look at a much deeper population of quasars and allow us to look at a lot more of these systems, as well as then these targeted searches that are going to follow up on, good candidates for having supermassive black hole binaries. The other things that we're excited about for future directions for this kind of work would actually be in LISA, looking at lower mass binaries and lower luminosities in tandem with Vera-Rubin LSST, as well as just the improved coverage of, frequency here. As I mentioned towards the beginning, we need nearly decade-long baselines for, pulsar timing array band. But in LISA, we would need much shorter baselines, since we would expect to see a lot more of those oscillations in a relatively short period. All right, thank you all so much. And I hope you enjoyed my talk.
All right, thank you, Andrew. That was great. Yeah, really enjoyed that talk. All right, are there any questions from the crowd? Well, you briefly touched there at the end on the one I was going to ask, which was how would this extend to LISA? Because yeah, I was very interested to see, do you have any intuition? You list this as something that you want to explore, but do you have any intuition on whether these same correlations might hold as we look towards the lower mass binaries, or based on those charts, do you have any expectation on how it might change?
It's a little bit hard to say right now. So my intuition, just based on this chart, might be towards it not quite holding. But that being said, there's a lot of things that we have to consider when we're looking at this kind of downward slope right here, including the fact that I've cut this off at luminosities above 10 to the 45 ergs per second. So fairly bright quasars that we're looking at here, and that's just to match the CRTS sample. I think it would be interesting to actually take this down to lower luminosities, and I haven't actually looked at that since we've been hesitant. Since we, don't want to go too far beyond the actual catalog that we have. But yeah, that might be something that I should actually sit down and just say what happens if we just take the luminosities lower. Yeah, so I guess that's a long way of saying I'm not sure, but that's a really good question.
Yeah, fair enough. I'll be interested to see where it goes. All right, any lingering questions out there? If not, we'll take, well, I guess this session technically ends, but we move on to 15B2 in 10 minutes. So for those of you who are going to stick around for that, I'll see you guys in 9 minutes. For anybody who's heading out, thanks for coming. Hope you guys have a good rest of your night. Thank you to all of our speakers, of course. All right. Well, I will, okay, let's go ahead and get started. I'm sure more people will trickle in over the next couple minutes, but let's go ahead and get started. So welcome everybody to this session. I think it's the last session, if I understand correctly. So let's go ahead and start. And we're going to hear Alexander first talk about the outlook for detecting gravitational wave memory effects with ground-based detectors. Take it away.
All right. Yes. So I'm Alex Grant, and today I'll be talking about some work that I've been doing with David Nichols at University of Virginia on the outlook for detecting these gravitational wave memory effects. And this is work that's based on a currently published paper. For convenience, I've just put up the archive number, which contains, there were some significant errata relative to when it was originally published. And in addition, the code to actually generate all the results in the paper is now publicly available. So before getting into the detection of gravitational wave memory, what is the gravitational wave memory effect? The idea is that for observers, if you had just a pair of observers that were freely falling with no relative velocity, a burst of gravitational waves would cause a net change in their separation. And you can think of this either in terms of these, idealized observers, or you could think about them this in terms of a change in the metric in some gauge. And the idea is that if you were to plot a component of the metric as a function of time in this gauge, the component would look not like this red curve that returns back to its initial position, but there is a final offset or a finite offset between early and late times. And this is a relatively small effect. It's currently unmeasured. People are currently looking for it in ground-based detectors and also in pulsar timing arrays. The prospects for detection are quite good for space-based detectors like LISA. For ground-based detectors, it's predicted currently that it would take about 5 years of LIGO and Virgo detection at their 0.4 sensitivities. And this talk is, well, the first half of this talk is about updating these estimates because 0.4 is not going to last for 5 years. The second part is I mentioned gravitational wave effect or memory effects. That's because there's more than one. So another one is the so-called spin memory. The idea here is that if you have two observers with some initial relative velocity, in addition to their separation, the radiation will cause a change in their position that is related to not just a change in the metric, but also some time integral of the metric. And if you look at this time integral of the metric on the sphere, do an electromagnetic decomposition in terms of spherical harmonics, the spin memory is the magnetic part of this, which is the dominant piece. And this talk will also address the question of, can future detectors see spin memory, which ends up being a much smaller effect. Now, why do we even care about any of this? Well, it turns out that these effects are relevant for astrophysical sources. The asymptotic Einstein equations imply that you can derive formulas for the change in the metrics, so the displacement memory effect and an integral, so the spin. And there are two contributions for each. So that there's these delta M or delta N contributions, which are related to changes in source properties. This is the so-called linear or ordinary memory effect. And there are also pieces that are quadratic in the gravitational wave amplitude. And these probe nonlinearities in the propagation of gravitational waves. So it's really testing the strong field regime, but not the strong field in the sense of, it's a binary merger, so there's strong field gravity there. It's actually strong field as the gravitational waves are propagating out to infinity. Now, how do we actually measure the memory? Well, as as is done for a variety of other types of effects, you can do a type of Bayesian hypothesis test. You can ask the question, does a signal favor either just the oscillatory waveform or a waveform that is both oscillatory and has a memory component? Now, this Bayes factor is a relatively hard to compute thing, but there is sort of a limit in which you can get away with computing something far simpler. So if you assume, first of all, that your memory model is the correct one, and as a slight technical assumption, if you assume that when you do parameter estimation, that the distribution of parameters is sharply peaked around the true value. So as an example over on the side here, this is a case where it's not sharply peaked, it's sort of bimodal. There's a peak here and a peak there. But if it's sharply peaked, so it looks more like this around the true parameters, that it turns out that the log of this Bayes factor can be easily computed on average over the noise, and it's just related to the square of the signal noise ratio of the memory. And if it looks something more like this, where it's bimodal, it will go like SNR to the fourth power, and if SNR is small, this is something that can be neglected. Now, because the Bayes factor is, you can think of it like a probability, it's multiplicative between multiple independent events, and so you can add up its log, so the SNR is squared, and that gives evidence for the memory in a whole population of events. And this is a way that was proposed to actually measure the memory, since it wouldn't be seen in individual detections in LIGO. Now, there's one thing that I somewhat glossed over, namely that entire procedure that I just described assumed that there was a way of splitting the waveform into a piece that is purely oscillatory and a piece that is non-oscillatory and associated with the memory. And as I previously described on previous slides, the memory effect is associated with some change over a burst of gravitational waves, a change in the metric, the total integral of the metric over the entire waveform. How do you pick its intermediate values? What's a good choice of this memory as a function of time, the memory part of the signal? And it turns out that there is sort of a canonical choice that is good in a certain sense. And it comes from looking again at these asymptotic forms of the Einstein equations and the formula for, say, the displacement memory. It turns out that this first part here associated with source properties is mostly oscillatory. It's related to like the change in the quadrupole moment of the source. And this piece here, the nonlinear piece, is the piece that results in the net change. So the choice that we use for the memory as the memory part of the waveform is exactly this nonlinear piece here. And a similar type of approach can be applied to the spin memory to acquire a so-called spin memory signal. Now, if you actually look at these parts of the waveform as a function of time, they're very small. If you plot the oscillatory part and all of the other parts of the signal on the same graph, in order to make them all comparable, you need to multiply the displacement memory by 10, the spin memory by 100. They're very tiny effects, and that's why it's important, why you need to actually stack signals from multiple events. So, but it ends up being the case that this is something that can be done, and it is actually detectable by current gravitational wave detectors. So this is a plot where I show the SNR as a function of time. Instead of choosing just one representative population, consistent with population models that are currently in use, I've chosen 300 and essentially computed statistics like the median over these different populations. And consistent with previous results in the literature, if you have your detectors maintain this 0.4 sensitivity for 5 years, yes, it seems that the displacement memory will reach this detection threshold. If instead you upgrade the detectors, after about 1.5 years to the 0.5 sensitivity, very quickly you see it. It only takes an additional year or so. In fact, you could also add in LIGO India, which might start, maybe 3/4 of a year after the rest of the detectors have joined O5. But even doing that doesn't really change these results too much. So that was the displacement memory. The story for spin memory is very similar, except this is a much smaller effect. So current detectors, even with the O5 upgrades, beyond design sensitivity, this is an effect that's too small to be seen. So instead, we considered Cosmic Explorer, which is a next generation, a third generation gravitational wave detector, hopefully coming online in the 2030s or 2040s. And as you can see, this is the spin memory SNR as a function of time. Once again, even in the case where there are only 2 cosmic explorers, it's possible that we'll have 3 of them, or 2 cosmic explorers and 1 copy of Einstein telescope. Even in the case where there are only 2 cosmic explorers, it seems likely that over 5 years we'll be able to measure the spin memory. And in fact, this estimate is a bit conservative, because this forecast is very sensitive to small or quiet events that are very far away. So it depends heavily on the population models that you use at high redshift. Here for this plot, I've essentially assumed that there are no events beyond a redshift of 1, which is almost certainly false. So this is essentially, you could think of it as a lower bound. One complicating factor, however, is that all that this shows is that there is a sufficient number of events that if you added up all of the SNRs, you could get a detection of the spin memory. This ignores, systematic errors, overlapping signals that might significantly change these results. Since we're looking at Cosmic Explorer anyway, which is significantly more sensitive, you could ask the question of what about the displacement memory in Cosmic Explorer? And it ends up being the case that for the displacement memory, unlike for the spin memory, where you again need to look over an entire population, for the displacement memory, there will be individual events in Cosmic Explorer where you can resolve the displacement memory. And that was also true for in previous literature. That was shown for LISA as well. And in fact, actually, we might see a few events that not only exceed the threshold for detection, but are very relatively high SNR for the displacement memory. And with so many events, it might be even possible to ask the question of, can you test GR with the memory at this point? I mean, seeing the memory at all is a test of GR in a sense, but an actual, parameterized test of GR might not be able to be done with the population. It might take individual events. So in conclusion, these displacement in memory, or these displacement and spin memory effects, these are non-oscillatory parts of the signal that probe nonlinearities of general relativity. They might soon, for certain definitions of soon, be seen either in O5 of LIGO Virgo Cabra for the displacement memory, or you could also see it for the displacement memory in individual events if you had Cosmic Explorer, or about 2 to 3 years of Cosmic Explorer, we'll see the spin memory. For future work, there's a question, especially for the spin memory, where things depend very heavily on the population at higher redshifts. How will these forecasts change over time as we learn more about the population? Moreover, there's the question of using other detectors, for example, LISA. Here, we used Cosmic Explorer instead of LISA simply because the population for Cosmic Explorer was better constrained. But in principle, one could do a similar type of analysis for LISA and the spin memory. And then there are also other smaller effects, smaller even than the spin memory, known as center of mass memory. And there's also these so-called higher moments of news. And one could also ask, are these measurable? What type of detector would be necessary in order to measure them? And again, to reiterate, I have up the paper and also a link to the code that, of course, you guys can't click on now, but hopefully when you have the slides, you can. And thank you.
All right, great job. Thank you, Alex. Any questions from the audience on that? So, question I always have about memory, a lot of what I think about and what a lot of the talks, some of the talks were about today, is what we miss by neglecting certain features and what, how we might skew parameter estimation or tests of GR. And so memory being another effect that we often neglect when we're doing our modeling, what might we be missing out on by doing that? That
is a good question. It's not a question that I know the answer to, essentially. There's an argument that I've heard that not modeling the memory won't be, well, yeah, I have no real sense. There's the one thing about the memory, if you don't model it, the problem, it might not change things too significantly because the memory, since it's non-oscillatory, looks very different from the rest of the signal. So in that sense, it might not be confused for something else. But I think there has been some work on this, and I think there are effects of that arise if you do neglect the memory.
Yeah,
I just don't know the numbers.
Are there any systems? So while it might not mess with the parameter estimation of the waveforms themselves, I wonder when we are dealing with overlapping and stacking, like overlapping signals and stuff, I wonder if the memory effect could, if there are types of events that are, less oscillatory in nature, that it may get tangled with.
Yeah, so there are yeah, so it for compact binaries, the memory effect is always going to be sort of the small. It's going to be maybe about 10 times smaller than the oscillatory part of the signal. That's always going to be the case. It's always going to be a subdominant effect. It might be on the order of higher order modes in terms of magnitude, or it almost certainly is. But it's also non-oscillatory, so it interacts with the interferometer in a different way.
Sure.
But the point that I was going to make was that there are different types of events. So if you have hyperbolic encounters, for example, the memory effect is much larger than the oscillatory part of the signal, and it completely dominates the signal.
Interesting.
So those are the types of events that you really do need to care about the memory. But for the most part, memory is an effect that's sort of comparable to higher order modes, at least in terms of magnitude.
Okay, great, thank you. Any other questions? All right, then let's go ahead and swap over to Hanyan. If you want to go ahead, let's see, remove spotlight. Yeah.
Hello, everyone. My name is Han Yan, a first-year graduate student from Peking University. The topic of my presentation today is calculating the gravitational waves emitted from high-speed sources. This talk is based on a published PhD paper, and this paper was at first actually my undergraduate thesis under the guidance of Professor Xian Chen. My talk will be divided into 3 parts, and in the first part, I'll give a brief introduction of the background and motivations of its work. At the beginning of this part, I would like to emphasize that our main result is that we deduce a new formula to directly calculate GW from source with high center of mass velocity and directly in the observer's frame. This procedure is highly similar to linear potential in electrodynamics. So the problem is, how did we deduce this formula? And most importantly, why did we consider to do this thing? Actually, our research first came from the problem of detecting the velocities of GW sources. As we know, in electromagnetic wave observations, we can determine the velocity of the source by classic Doppler effect and characteristic spectral lines. However, in GW observations, there are several effects interfering this procedure. As we know, there are cosmological redshift, gravitational redshift, environmental effect, and of course, classic Doppler shift. Especially when we take cosmological redshift into consideration, we actually cannot simultaneously determine the mass and velocity of a GW source if we will only consider constant center mass velocity. This result has several effects. On the one hand, many people turn to consider the acceleration effect from long-term frequency shift observation, like in LISA. On the other hand, it also gives us a chance to reconsider the complete theory of calculating the GW from a high-speed source, because such a complete theory is actually not quite clear, especially when we also take the center of mass acceleration into consideration. Another motivation of this work is the possibility of the existence of supermassive black hole, of high-speed GW source in the universe. As most of us may agree, there are many supermassive black holes in the universe, and according to several researches by Nicolas and Chen, there is possibly a kind of GW source called EMRI, in which a binary is approaching a supermassive black hole. This binary can have pretty high center of mass velocity if remind binding. So after telling you the motivation of this work, I would like to briefly talk about what have people already known about this issue. Actually, mostly commonly known result is the so-called Lorentz transformation of gravitational waves. It is actually based on the relativistic transformation of second-order tensor in flat spacetime, and its result says that the center of mass velocity of the GW source represents a different four-wave vector and several different polarization vectors. Several years ago, one of our authors, Alejandro TorresOrjuela, tried to examine his problem from a different view. He considered the problem in the center mass frame of the source, considering the GW detector with high speed and using the assumption of plane wave. He calculated the response of the detector and find that the final result is actually completely consistent with Lorentz transformation. As a comparison, our new result try to directly calculate the GW tensor in the observer's frame, and this idea is actually highly motivated by the inertial potential in electrodynamics. As we know, there are also two methods to calculate the electromagnetic field in for a source with high speed, and this is actually an analog of it. And as we will talk, our formula, although is consistent with Lorentz transformation numerically, it may have several advantages for certain cases. Next, as the second part of this presentation, I would like to briefly talk about how we deduced that new formula. We started with London-Riff's formulation and including a complete version of effective energy momentum per Stowe tensor. After writing down this wave equation 1, we can directly integrate it as we always do in the center mass frame to deduce quadruple formula. So although in this work, we calculate it in the frame of observer. We next use a different type of multiple expansion. And I would like to emphasize that in the several next pages, I both print the formula we use and the formula commonly used in the central mass frame to deduce quadrupole formula. As you can see, in our new multiple expansion, we define several new retarded time, and in the integrand, or the spatial coordinates of the components of the source, subtract the spatial motion of the center of mass using one of the retarded time and center of mass velocity beta put by hand. We next also do the integration by parts, and this second step is actually quite simple in center mass frame if we only need to consider the quadrupole terms. However, here we need to leave several more terms, and we also define several new multiples and Q, and their definitions are recorded in the next page as equation 5. And as you can see, the spatial coordinates also subtract the center of mass motion. As the last step, which you might be more familiar with, we use the conservation law of the effective energy momentum tensor to transform it to a second order time differential form. And as you can see, our result is also similar but different with the formula used in the central mass frame. Next, the key point is our final key formula. I have omitted a lot of details to deduce this formula, and you can find all of them in our paper. This formula might look like quadrupole formula for some of its characteristics, like in the first line, but of course it's much more complex, and I would like to summarize several of its properties to let you better understand it. The first point is that, as I have said several times, this formula is calculated completely in the frame of the observer, and all the quantities of the source are measured in this frame, including these spatial coordinates and velocities. The second point is that although in these spatial coordinates, they all subtract the center of mass motion, as you have said, you have seen in its definitions in previous page. All these velocity don't subtract the center of mass velocity, and they are actually the real velocity in this observer's frame, including the center of mass velocity. And you need to add them to this like VI, VJ, and gamma to correctly use our new formula. The third property of this formula is that, as you can see, before each term, there is a factor similar to 1 divided by 1 minus n dot beta, and this factor is similar to what you might be familiar with in linear potential. So after telling you the main result of our research, in the third part, I would like to briefly talk about several of its applications and also give some discussions. The first point is certainly that we want to know the relation between our new formula and Lorentz transformation of gravitational waves. We use Wolf engine to do this, and the symbolic calculation shows that our formula is actually consistent with Lorentz transformation for single frequency motion case. We next consider a slightly different case in which a nickel mass binary is moving with a high center of mass velocity. We calculate the response of detector and compare it with a formula from Alejandro's paper, which is actually also consistent with Lorentz transformation. These two results match each other well, as shown in this figure. Next, we also consider a rather more different case in which a binary is scattering with each other with a high center mass velocity, possibly happening in an AGN disk. A certain component of the GW tensor is plotted in this figure with time. Finally, in the last page of my presentation, I would like to do some summarize. The first part is the significance of this new formula. The first point is, of course, we confirm the results of well-known Lorentz transformation, although we use a completely different method, directly integrating the wave equation in the observer's frame. And it's actually quite similar to Nicolas potential. The second point is that by using this new type of multiple expansion, we certainly have some deeper understanding of it, because this method was always used in the central mass frame or in the frame in which all the components of the source have relatively low velocities. The third point is that our formula might have some numerical advantages, although we didn't prove it in this presentation. This point means that if we can directly get an orbit with high velocity, rather than first calculating the orbit in this center of mass frame, we can directly use our new formula rather than do the Lorentz transformation. We would also like to summarize several points that we might do in the future after this research. The first point is that we can calculate higher orders of the gravitational waves because we only consider the quadrupoles in this work. The second point is that we can carefully consider the central mass acceleration of the gravitational wave source. However, these two points both have several difficulties. The first one is highly related to PN calculation, and of course, it's not quite easy. The second point, however, might involve much more problems, especially when we carefully consider the causation or the energy momentum tensor of this center of mass acceleration of the GW source. It might also involve the wavelength problem, which was carefully discussed in Bonetti's paper. So my presentation is ended here. Thank you for your listening, and I'm happy to take your questions.
All right, thank you so much for that excellent talk. Are there any questions from the crowd? Okay, I don't see any. You kind of touched on some of this at the end, but I was just kind of wondering what are you most excited about in regards to having this new equation, this new formula? What are you most excited about being able to do with it? Or yeah.
That's a good question, because as I have said, the numerical result is actually consistent with Lorentz transformation. For me, what is most excited is that we successfully apply a new version of multiple expansion, and the result is actually also has some similarities to Nicolas potential. At first, at the beginning of this research, we try to do a comparison between electromagnetic wave and gravitational waves. And because of many reasons, this comparison is not that easy, but we certainly do some small contribution to this calculation or this method.
All right. Thank you so much for that. All right. We'll go ahead and oh wait, Neil raised his hand. There we go.
Yeah, so I actually had a quick question about this. Sorry if this is a naive question. In the beginning, in slides 2 and 3, when you're talking about the sources, high redshift and Binaries, are there any population models about like the relative, do we expect more from high redshift or Binaries, even if this is really model dependent?
Although this is actually not the key point of this research, I certainly know something about it because Professor Chen is my supervisor. According to their researches, although it's a calculation maybe several years ago, they might be most likely 1 to 100 rate of BMRE in the future space-based observation of GW. Although the detailed event rate is certainly related to dynamic models. I think you can check it in several papers about BMRE itself.
Okay, awesome. Thank you very much.
Thank you.
All right, then if people come up with questions later, feel free to put them in the chat. Otherwise, Neil, if you want to go ahead. Oh wait, Otto has a question. Go ahead. Never mind. We've still got 3 minutes.
Yeah, thanks a lot, and sorry for the late hand up. Yeah, I want to, this is a very naive question, but since it's about high-speed sources, could you maybe say a couple of words about what your expectation for observing some of those high-speed sources would be?
Okay, certainly. The first thing is that why we are interested in high-speed sources. The key point is that it's possible that we can simultaneously observe different frequency band from this kind of system, because as you can imagine, when a binary is approaching a supermassive black hole, the binary itself can emit GW, and the center of mass of the binary with the supermassive black hole can also emit the GW, and that's why its effect is quite interesting, and we can deduce more properties of the system from this kind of observations. I don't know if I get your question.
Yeah, I see. And so I guess that the question is sort of regarding more kind of this what you marked as 1 or I in here in the graph is you know how likely it is to actually have formed a binary black hole close to one of these supermassive black holes.
So
I was wondering sort of what your expectation is for the both the sort of how likely it is, and also what kind of velocities we're typically talking about.
As I have said to another listener, the most likely the event rate of this kind of system is probably 1 to 100 for normal EMRI system. But this calculation is actually very early, and I don't carefully take care of it recently. The second point, let me think. the second point is the velocity of this binary, right? As several researchers have said, the central mass of this binary may approach like 0.1 speed of light for some extreme case, although mostly it cannot reach such high velocity. It actually,
thank you very much.
Depending on whether this binary can remain binding, and it's a dynamical thing.
Okay, thank you.
All right, thank you guys very much for that great discussion. All right, we'll go ahead and have Neil go ahead and share your screen.
Hi everyone, my talk is about inferring neutron star properties with continuous gravitational waves. This is some work I did supervised by Karl Wette and Susan Scott from the Australian National University. And I put links there to our paper and to the archive preprint. But going straight into it, what are we interested in? What is the scientific motivation? So we're interested in knowing more about neutron stars. As you may know, that these are the collapsed cores of massive stars. After they finish, they can no longer sustain themselves with nuclear fusion. They form neutron stars after a core they form neutron stars. And they're particularly interesting because inside their interiors, there are pressure and density conditions that are really quite extreme. They're things that we cannot emulate on Earth. And so understanding the physics of a neutron star is to be able to probe a density and pressure regime that we can't otherwise understand in any other way, and especially not on Earth. And we definitely know neutron stars exist because they are the pulsars that we have heard so much about from nanograv and from the PTA community. So, neutron stars, we know some things about neutron stars from pulsar observations. But the problem is that we don't know much about their interior physics, which was exactly the regime that we wanted to know most about because it was motivating our interest in these systems a lot. And in particular, not only do we not know much about their interior physics, but we actually have very few measurements of very basic neutron star properties. So things like their mass, their radius, their moment of inertia, really fundamental things about these objects we don't understand very well. We have a few measurements from things like NISA and a few exceptional systems, but it's not much is known. And a kind of hand-wavy, intuitive explanation for why this might be the case is because if we are trying to understand these systems from pulsars and from the electromagnetic observations we have of pulsars, these are dominated by the processes on the surface of the neutron star, which is opaque. And so even this is dominated by a thin layer, which does not contain much of the mass, and by definition is not the interior of the neutron star. So it's dominated things by processes on our atmosphere and the outer crust, as I have on the schematic on the right, but not much about its interior physics. And so this might explain why electromagnetic observations are not our best tool to be able to understand neutron star physics, and in particular, the interior physics. So if only we have some observational medium which was primarily dominated by the behavior of matter, and the interiors of objects. But gravitational wave comes to our rescue. And in particular, we are interested in spinning isolated neutron stars, and not only the wonderful BNS observations that we have Why is this the case? Because in just a very intuitive way, we are particularly interested in the kind of ground state behavior of these neutron stars, the behavior of their physics when it's not highly perturbed, but when it's at equilibrium in these pressure and density regimes. So CBCs are not the ideal laboratory for this because the physics is behaving on very dynamical timescales. So we really want to know more things about spinning isolated in neutron stars. And these types of systems emit a type of gravitational wave, which are known as continuous gravitational waves. So these are what we call quasi-infinite, quasi-monochromatic gravitational waves. All that means is these neutron stars spin for a really, really long time, like mega years or longer. They are almost monochromatic. The frequency is very close to it evolves on a very slow time scale. And so the continuous gravitational wave is almost a pure sinusoid in the rest inertial frame. So these are the particular types of gravitational waves we're interested in. No known signal has been detected yet, but the LVK does a lot of analysis, both targeted, directed, and all-sky. Essentially, what this means is looking for different types of neutron stars, whether they are known from pulsar observations or not. And we have upper limits that we place and continue to get better and better as we get better and more data. So that's the kind of scientific motivation behind the work. We did two main parts. We did some theoretical work, which I'm now going to step through. So we're interested in understanding how a continuous gravitational wave observation would actually be able to understand or measure properties of the neutron star itself. So we assume a continuous gravitational wave has been detected. This would be awesome news. Would be a first discovery. How would we use that first discovery to say something about the neutron star that emitted the signal we're detecting? So what are we starting with? We're assuming that from this measurement, we get spin down parameters of the neutron star. So this would be, for example, its frequency and its first and second derivatives of frequency. And this is just because when we measure a sinusoid or the phase of the continuous wave, these are parameters of the signal. We would also get what we call the characteristic strain amplitude, or essentially just the strength of the signal. And we're also, in our work, considering the distance to the neutron star would be known. And this does not come from the continuous gravitational wave itself, but we think it's quite reasonable to expect that this would come with a first detection. Why is this the case? This is because with the first detection, we would localize this, we would get the sky position of the neutron star emitter to a very high precision. And from that, we think it's likely that you get the distance, either because by focusing on that sky position, you would be able to detect some electromagnetic signal, which otherwise you would have been too faint to be detected if, in an all-sky survey. Or instead, if that sky location corresponds to a particular galaxy, etc., it is likely that that neutron star exists within that galaxy. And so you can take the galaxy as a proxy for the distance to the neutron star itself. So with assuming these measured parameters, we wanted to be able to say something about the neutron star emitter. I'm gonna, given that this is the very end of Amaldi, I'm not gonna force you to sit through all this math, so I'm gonna skip to the derivations. It's in the paper if anyone's interested. But essentially, I'm just gonna present our results, which is we found you can measure 3 properties of the neutron star. Those 3 properties are the moment of inertia, ellipticity, and the magnetic dipole moment. And I've shown how those depend on our observed parameters in those 3 equations. So there are 2 things that I want you to take away from the slide. The first thing I want you to take away is that it is possible at all to infer these 3 properties. Because prior to this, and in particular, if you don't have a distance measurement, there are actually a lot of degeneracies such that it is very, very difficult to say anything about the neutron star emitter. And in particular, measuring these three properties with any observation, electromagnetic or with any type of gravitational wave, is very difficult. As I flagged before, we don't have many observations of neutron star properties itself. So being able to measure anything is, quite nice to be able to advance our understanding of neutron stars, so that we have more measurements of them. That's the first takeaway I want you to have from this. The second takeaway is to note that condition that I have on the bottom. So in order for the system to be solvable, in order for the math to work out, for Mathematica to be happy, essentially, we have that this parameter, f multiplied by f double dot divided by f dot squared, which in the community is already a known parameter. It's the breaking index parameterized by n, has to be within this certain range between 3 and 5. And actually, it's very, very good that we have this condition, and it is a great sanity check. And the reason why is because if you consider a neutron star, which is just emitting energy via continuous gravitational waves, which are quadrupolar in nature, then it is known from theory that your breaking index should be 5. If instead you consider a neutron star, which is only emitting electromagnetic radiation, it's known that the breaking index is 3. So if you have this neutron star, which we assume is emitting some combination of continuous gravitational waves and electromagnetic radiation, then it is completely natural to assume that the breaking index should be between 3 and 5. And in fact, this comes for free in all of our maths. And so this is a great sanity check. This makes complete sense. So now we have this great theoretical framework. The next question is to do some simulational results and to ask the question, are the errors small enough to actually constrain neutron star physics? Or are you going to get something like 100% error bars such that, nominally these things are measurable, but, you can't say anything meaningful as a result of them? And so this is what we wanted to consider. So what we did is we performed some Monte Carlo simulations. And what these was we considered an individual neutron star. We considered with some parameters that we think are physically reasonable. We calculate the uncertainties of the observables, parameterized by a Fisher matrix. And we sample an individual observation as drawing from a Gaussian with the, centered around the known injected parameters with some width parameterized by the uncertainties. And then we repeat these over and over again. And for each one, we consider how the calculated parameters, so the moment of inertia, ellipticity, and magnetic dipole moment, our calculated value has an error in comparison to our injected values, and we consider how the distribution falls over a large sample size. So just for posterity, I have included the parameter range of neutron stars that we've considered. We chose this to try to be as agnostic as possible over a range that is also feasibly detectable. And what do we find? So the first thing I want us to consider is how the error for a single neutron star evolves as a function of how long we have observed the continuous gravitational waves, because these are things we observe for as long as our detectors are running. So the longer we detect them, the more information we have from continuous gravitational waves. So I've injected a particular neutron star here, and we see, as we expect, the error scales with observation time. The error gets better. So you see here how the ellipticity changes with observation time. And you see that it decreases up until some points that the error no longer is saturated and no longer gets any better. And the reason why this is the case is because here, the extra observing time improves the properties measured by the continuous gravitational waves, but the distance, which I flagged earlier, is from electromagnetic observations or from a galactic catalog. This does not depend on the continuous gravitational wave observation time. So at some point we're saturated or limited by that amount, which I've taken here to be 20%. And so it makes sense that we get some bound which we cannot beat. I now am interested in considering how this depends on the breaking index. So I flagged before that breaking index can be between 3 and 5. Is there a part of the parameter range which is better or worse? What we see here is that close to the boundaries between close to 3 or 5, there are some divergences in some of the parameters. We have defined a new quantity, the relative error, which essentially just normalizes out that saturation level I flagged before, such that a relative error of 1 means that we're only getting things from the distance uncertainty. And so we get pretty good results in that intermediate range between 3.5 and 4.5, let's say. But on the boundaries, things are bad. And this makes complete sense, because if all the energy is lost to electromagnetic radiation, then it makes sense that we can't say much from continuous gravitational waves, which are very weak. And on the right-hand side, close to n equals 5, if a neutron star loses all its energy to continuous gravitational waves, it doesn't have much of a magnetic dipole moment, and so it's very hard to infer that particular property. The final thing I've done is considered how it depends on f dot, and our breaking index. So this is a very complex plot. The rows correspond to the 3 different parameters which we can measure. So the top row is moment of inertia, the middle row is ellipticity, and the bottom row is magnetic dipole moment, and the relative error in those 3 parameters. The columns correspond to the different breaking indices, possibilities. And for each little heat map I've got there, the x-axis corresponds to frequency, the f dot, the y-axis corresponds to f dot. All I want you to take away from that is that in most of the parameter space, the color is green or yellow. And you can see from that the color bar, that green and yellow is close to 1. And close to 1 is a very good error, or the error is almost all from the distance uncertainty. And so the overall message I want you to take away from all these heat plots is that we've checked a lot of the parameter space, and in most of the parameter space, the error is quite good. And we're getting within observation time of 1 year to becoming saturated by the distance uncertainty. So in summary, the things I want you to take away from this talk is we create this theoretical framework such that it's possible to infer some neutron star parameters using either a simultaneous observation of both CW, continuous waves, and electromagnetic, or if the distance is known in other ways. Secondly, that in most of the parameter space, the error is dominated by a distance uncertainty, but there are some regions, for example, if the breaking index is very small, it is very close to 3, where the error is large from the continuous wave parameters is larger. Thank you, everyone. I hope everyone had a very enjoyable Amaldi. I hope I didn't make that week longer than it needs to be. I'm happy to take any questions if anyone had anything.
All right, great. Thank you for that talk. Any questions in the audience? I don't see any hands up yet. So I was just wondering, and maybe you maybe I missed it, or maybe you talked about it a little, but what's the actual prospect of observing these with next generation ground-based detectors, and what's the prospect there of us actually seeing some of these events and understanding them and studying? I mean, you did a thorough error analysis there at the end, clearly, but I somehow missed some of the actual connection into the detectors and whether this is actually something we'll likely see.
So I think in our paper, we tried to be as agnostic, let's say, to the detectability, because we didn't want, there's a lot of work on detectability, and that's not what we focused on.
Sure.
Beyond the scope of our paper and more broadly, I think within next generation, the prospect is kind of within the community thought to be pretty good, especially amongst ET, etc. We are optimistic, let's say, within 04 and 05, as we get more data and data with better sensitivity. We are really hopeful that there are especially some sources that we think we have very good prospects on. But this is kind of one of those things that until a first detection is known, we are kind of shooting in the dark. So sure. We do think we are able to quantify based on getting these better and better upper limits, and having these upper limits beat certain naive expectations, let's say. But until a first detection, people can debate endlessly about exactly what sensitivity you think you need to get something.
Sure, makes sense. All right. Any more questions, or are we wrapping it up? Okay, well, I'd just like to thank everybody, thank all of our speakers, and thank all of you guys for attending, and wish everybody a great weekend. Thanks again to all of our speakers.